So we say SU2 is now we discussed about this group SO2 group in some class. SO2 group means 2 cross 2 orthogonal matrices with determinant 1, and we have seen that it is parameterized by this thing. This is one kind of parameterization only. Because of S, we have taken this thing. If we leave S, there can have another kind of parameterization with this minus sign coming to this side, but that will not have determinant plus 1. So this is the rotation matrix in 2 dimension. Now you can think that in 3 dimension SO3 you want to write SO3. How many parameters do you need to write SO3? Because NC2 n into n minus 1 by 2, 3 parameters. For this you need 1 parameter. You need 3 parameters for SO2 also. Now, okay, let me tell you this. Now, these 3 numbers x1, x2, x3, which earlier you were seeing in terms of, you are giving a meaning that it is a vector x in real space, and corresponding to these 3 numbers you can associate a traceless Hermitian matrix in this space. They are connection by 3 numbers. The same connection now is being translated to SU2 and SO3 homomorphism, because they are corresponding to every U there is a R. That means if I tell you 3 numbers, you will be able to write a SU2 matrix. We have seen that, how to the parameterization of SU2. Now if I tell you this same 3 numbers, you can construct another SO3 matrix. Clear? So by numbers they are connected like this. So say this needs 3 parameters, this needs 3 parameters. That means 3 real independent parameters. So you ask a baby about 3 real independent numbers who doesn't know anything about matrices, vectors, SO2, group theory, etc. He just tell you 3 numbers, 3 real numbers. He doesn't know complex numbers. Now out of these 3 real numbers, you can write down SU2 matrix. You said the alpha, beta, theta, those 3 in the parameterization of SU2. I have not shown you directly the parameterization of SO3. We will see this now. The thing is, let's see this first. You need 3 parameters to write an SO3 matrix. Now SO3 matrix is a rotation in 3-dimensional space that you have geometrically ascertained, confirmed. Now you can think that any rotation in 3-dimensional space, just you did in the study of Euler angles, or so you can think that suppose you have an XYZ axis. You first rotate a vector about x-axis, then y-axis, then z-axis. These 3 independently. So the new positions you get, it will have its component as x prime, y prime, z prime. And that is related to x, y, z by a matrix R. But this matrix R is then a function of the 3 angles of rotation about x-axis, about y-axis, about z-axis. These are not Euler angles, because Euler angles, if you remember, Euler angles, you first rotate with respect to z-axis in xy plane, then you rotate with respect to new x-axis in this new yz plane. Okay, so this moves up, this moves up. So this becomes z prime, this becomes y prime double prime. And then again, new axis you get x prime, y double prime, z prime. Sorry. In this plane, with respect to new z axis, you give another rotation. These three are conventional angles called Euler angles. So one is about x, sorry, first is about z, second is about the changed x, third is about the changed z. This way Euler parameterize the angles, but you can do it in a different way, about x, then about y, then about changed x, like that. Or to look more understandable, you can translate it with respect to first say x-axis, then y-axis, then z-axis, changed all these things. First x-axis you do a rotation. If you do a rotation about x-axis, y-z-axis will be changed. Then you do a rotation about the changed y-axis. Then x-z will be changed. Then you rotation about the changed z-axis. That is also another way of doing this. Now, if your x, y, z is the original vector, if you rotate it by an angle, what should I say? Just by an angle, say, about x-axis, okay, about an angle alpha. So what will be? So about x-axis you are changing by an angle alpha. That means y, z are changing. X is not changing. So basically it is a rotation in y, z plane only. And in one plane this matrix has this. So the rotation matrix in this case will be 1, 0, 0, 0, 0 cos alpha minus sin alpha cos alpha. You get it? It is immaterial whether you give it minus sign here or here, because alpha can be changed to minus alpha. So this is the result after rotation about x-axis. X prime remains x and y prime becomes cos alpha y minus sin alpha z. Z prime becomes sin alpha y cos alpha z, similar to two-dimensional rotation. Clear? So then with this changed vector, you give a rotation in, say, about y-axis by an angle beta. Then this object, multiply it, take it as a column vector. This object, you are doing a rotation about y-axis. So it will be cos beta 0 sin beta 0 1 0 minus sin beta 0 cos beta. So minus sign is immaterial. Here or here is same. Clear? So this will change only if you take this as a, if you do this product and write it as a column vector. So this will only, y will not be changed because y double prime will remain y prime here, because it is 1 here, 0 here. Only x and z will change, but according to the rotation matrix, by rotation by beta. Clear? Similarly, then you do the third rotation in the other plane, say xy plane. Sorry. Yeah, xy plane keeping z fixed. Then this whole thing will be multiplied by another matrix, which is cos gamma sin gamma minus sin gamma cos gamma 0 0 1 0 0 1. So this will be your changed object. Is it clear? So this is this into this into this into this. So three rotations in three different planes, you make it and obtain this. So this is one way of parameterizing the SO3 matrix by three angles, alpha, beta, gamma, rotation about x, y, z axis, I mean, in a perfect order. You can do it in other way around. I mean, you can do y-axis rotation first, then x-axis, then z-axis, but whatever it may be, there will be different parameterization. But then these angles will be different because same vector for these two given vectors, the angles will not be, I mean, these things. So, but three different angles. Okay. So what I am saying is that this SO3 matrix, which needs three parameters, three real parameters, okay, can be parameterized in this way in terms of three matrices, cos and clear? Is this clear? Hello.
Yes, sir.
Yes, sir. This is one parameterization of SU3. You can take other parameterizations also. You can, without doing, because this is not Euler's way of parameter. The Euler angles are not these angles for three rotations, because you can remember these Euler angles first with respect to z, then with respect to change z. In that case, here cos, this whole thing will be like this, but with a different angle. So that then also you have three angles, but three matrices. Clear? Now, so this is, you are doing a rotation of all vectors. I am telling in a reverse way now in R3. So there are different vectors x, y, z, w, v, u, like that. Take any vector. Now, for a given alpha, beta, gamma, for a given parameterization, so take this matrix is a fixed matrix. Now, operate this matrix on all the vectors. So all the vectors will be transformed to a new set of vectors, which all lie in this R3. Now, corresponding to this transformation, there is a matrix U, which is effective in this space. Corresponding to every vector, there is a vector x, and when you change this, do this transformation on x, is the reverse way I am telling. You do a R3, you can get one U. I don't know whether one U or two U. Clear? Just a minute. Now, what I want to find out is that for a given alpha, beta, gamma, what will be the corresponding U matrix? I want to write the U matrix in terms of the same alpha, beta, gamma. I know how to write a U matrix independently out of alpha, beta, gamma. But I don't know whether what is the relation between these three parameters with these three parameters. So I am fixing one particular parameterization, this, and or I could have fixed the other way of doing this, would have fixed U in this way and find out what is the corresponding SO3. Clear? Just a minute. Just a minute. Okay. Now, suppose, forget about, okay, leave this for this time being. Let us do the other way around, because that will be more, less, I mean, complicated. Consider a matrix U belonging to SU2. So it needs 3 parameters. So one way of parameterization of U, we have seen how to parameterize it, how a unitary matrix of order 2 cross 2 having determinant plus 1 can be written. If you remember, let me check how we have written that. How we have written that. We have written that like e to the power I alpha cos theta. It is the result of earlier class, sin theta minus, we have seen this parameterization of, derived this parameterization of this. You can check that UU dagger is 1 always. Alpha, beta, theta are 3 parameters here. You can, with this form, you can intuitively write any form with 3 independent parameters and can check if that satisfies this condition that UU dagger is equal to 1 and determinant U is 1, then you have obtained a parametrization. There can be infinite ways of writing this matrix. Okay. There can be other ways of writing this matrix. Let's actually, okay, can you wait for a minute? I have a problem. Actually, I am having some back pain. Okay, you with me, you do one exercise. Suppose I am writing down another way of parameterizing this matrix. Earlier class we did one parameterization, but suppose you don't, but that needed some algebra. It's the same straightforward algebra, but some long algebra. Suppose you bluntly write one matrix. Can you tell me, this is written in terms of one parameter. This is a simple matrix. Can you tell me whether this matrix is a SU2? Because its determinant is obviously 1 and you check it's unitary. It is easy to check. UU dagger will change these signs. So UU dagger will be 1. Clear? This belongs to SU2. Clear?
Yes, sir.
Now you write another matrix, because cos beta minus sin beta, cos beta, all the real parameters. This is also trivially SU2. Is this clear? Because this is a rotation matrix, SO2 matrix. But SO2 is a subgroup of SU2 because where elements become real and then dagger will become transpose. So you can call this, because this satisfies this condition, UU dagger equal to 1. UU dagger equal to 1 and determinant U is 1. This is the condition for SU2. It nowhere tells it can't be real. So an intelligent person can trivially take this also as SU2 group. Okay. Now you check these two matrices are linearly independent, because one cannot be expressed in terms of the other. One cannot be written as some constant into this. Am I right?
Yes, sir.
Yes. Now write a third kind of matrix of whichever way you like, which is not this, neither this. neither a linear combination of this. You understand my point? This is the intuitive way of writing down any parameterization. You can write infinite number of parameterization according to your bend of mind. So now I choose a specific way here. So let's write this. Cos alpha minus sin alpha cos alpha. This is same as the above matrix, so this cannot be. But I do one thing. I put a I here, I put a I here. Clear? If I put, not everywhere, only at off diagonal positions. Now check that this matrix has a determinant +1.
Yes.
Cos square. Yeah, and this is also unitary. And this is linearly independent of these two. These three are linearly independent because you cannot write this as a sum of these two. If you can write it, only then this coefficients has to be 0 always. That is the meaning of linear independence. So this is one. This is out of infinite number of ways. This is one way of writing this. So you have one parameter. Each is a one parameter way of writing. Now if you multiply them of any order. Now since determinant of A, B, C, the whole matrix is determinant of A into determinant of B into determinant of C. Therefore, their product will always have determinant 1 because each of them has determinant 1. Okay. Also, if a product of all three are unitary, their product also has to be unitary. Yeah. If U1, because unitary matrices forms a group, so if all three are elements of SU2, so SU2 is a group, so their product by closure property should belong to SU2, or you can check it also independently by
Sir, last determinant 1 হচ্ছে না তো?
হচ্ছে না?
Square alpha minus
হ্যাঁ?
না মাইনাস হয়ে যাচ্ছে, মানে 0 হয়ে যাচ্ছে, মানে cos স্কয়ার মাইনাস sin স্কয়ার হয়ে যাচ্ছে।
cos স্কয়ার মাইনাস sin স্কয়ার হচ্ছে?
হ্যাঁ, মানে
সরি,
cos স্কয়ার প্লাস i স্কয়ার sin স্কয়ার।
প্লাস আই হলে কি হবে? দেখো তো প্লাস আই হলে
ইউনিটারি হবে না, ইউনিটারি হবে না,
হবে না?
না কারণ যদি কমপ্লেক্স কনজুগেট করে ড্যাগার নেন তাহলে মাইনাস আই সাইন আলফা মাইনাস আই সাইন আলফা এই টাইপের হয়ে যাবে না?
দেখো তো চেক করে দেখো একটু।
স্যার ওইটা মাইনাস থাকা, এই দুটোই মাইনাস করলে কি হবে? না তাও মনে হচ্ছে হবে না।
না দুটোই তো হবে না, দুটো মাইনাস হয়ে যাচ্ছে অ্যাকচুয়ালি।
হ্যাঁ, একটা সেমি রাখতে হবে।
এটা হচ্ছে না SU2 cos স্কয়ার আলফা ভুল করলাম আমি। cos স্কয়ার আলফা
অ্যাকচুয়ালি একটা সাইনে আই যদি নেন আর একটা কসে যদি আই নেন তাহলে হয়ে যেতে পারে।
হ্যাঁ,
একটা সাইনে যদি আই নেন আর একটা কসে যদি আই নেন তাহলে মনে হচ্ছে হয়ে যেতে পারে। দেখ
তাই কি? এক সেকেন্ড দাঁড়াও তো, একটা জিনিস হচ্ছে। হ্যাঁ বলো।
আচ্ছা, দুটো যদি প্লাস আই নেন, মানে যেটা আপনি লিখেছেন এখন, তো তাতে ইউ ডাগার তো 1 আসছে যদি দুটোই প্লাস আই থাকে।
একটু চেক করে বলো আমাকে, আর কেউ ক্রস চেক করো। দুটোই প্লাস আই নিয়ে দেখো ইউ ড্যাগার 1 আসছে কিনা, whether ইউ ড্যাগার is 1 or not.
হ্যাঁ স্যার, দুটো প্লাস আই নিলে ইউ ড্যাগারটা আইডেন্টিটি আসছে।
হ্যাঁ আসছে।
Okay, then it is correct. আদার যে পাচ্ছিলে না সে পেয়েছো শঙ্খ?
করছি আমরা
করে বলো, কনফার্ম করো।
হ্যাঁ স্যার চলে আসছে আইডেন্টিটি।
Okay, so sorry, তাহলে minus I না plus I হবে. Okay, so then it is SU2. Then their product is a representation of a parameterization of SU2. Clear? So in this way you can choose other ways of writing this. So you can choose e to the power minus I alpha here, e to the power I alpha here, then choose another matrix like that. Up to you. But I have chosen this particular parameterization to show you, because in different ways of parameterization, it becomes easy to in a particular parameterization something becomes very easy to show, because that is the need for, because like it is like choice of coordinate systems. For some systems you choose Cartesian, for some solving some problems you choose polar, depending on what kind of system it is. But for what I am going to discuss now, let's choose this parameterization, because once you choose a parameterization and in terms of parameterization find something, and then if you can tell that about that group, then this group is independent of which parameter, that statement about that group is independent of which parameterization you choose. Okay, so remember this. So I will come back to this slide later, but suppose this is another way of parameterization. This is one way of parameterization, this is another way of parameterization, and we have seen how just a minute. We know how a SO3 matrix is parameterized by product of three matrices. Okay, so I'm not writing it here. It is written in the other slide. Now look at this. So this is page number. Actually, these calculations are so big, you need a big space. Suppose you have suppose this matrix. Suppose X belongs to this stage 2, and you have done this. X prime is equal to U X U inverse. Okay, now X prime also belongs to this stressless Hermitian matrix. That means X prime you can write as X I prime sigma I. That is the rule. In this matrix you can write in terms of this, where there is a sum over I. Okay, U here, this is X, you can write Xi sigma I U dagger. U inverse and U dagger are same. Sorry, you can write it U dagger. Okay, so this is the relation. Now see, if I use a particular parameterization of U, say this one. Okay, if I use a particular parameterization of U, say this one, U will contain, their product will contain, each term, a 2 cross 2 matrix will contain some complicated, after this multiplication, whatever it is, alpha, beta, gamma. So U is a 2 cross 2 matrix involving its parameters. U dagger is also its dagger, and this is this. Now this equation will help you to write x1 here, is because if I can write this entire matrix in these terms, in terms of these unprimed objects, as a linear superposition of Pauli matrices in this side, then their coefficients should be equal to x prime. Okay, and this coefficient should be x1 prime should be something I can relate it. Coefficients of sigma 1 here and sigma 1 here should be same. Coefficients of sigma 2 and sigma 2 here it should be same like that. Clear? So that will help me to write down x1 prime, x2 prime, x3 prime in terms of x1, x2, x3, where u elements will be there in that expression and u is written in terms of its parameterization. But we know that the relation between x primes and x should be connected by a rotation matrix. So in that sense, I can obtain the elements of the rotation matrix in terms of the parameters of this u, one fixed parameterization of u. Do you get the point?
Yes, sir.
Okay. So since it is a complicated, I mean not complicated, it is a cumbersome calculation. Let's choose, okay, this form of u. Okay, so let's choose something u. So whether you choose product of this as a parameterization or product of this as a parameterization, see, u must always be of this form, to be very simple, in a simple way. A, B, minus B star, A star, where mod S square plus mod V square is equal to 1. Instead of writing all this complicated parameterization, to do it the calculation, we have written this C, that this is the general another way of parameter, but this we don't call it parameterization because we have to explicitly write another equation here. So see that its determinant is 1 because determinant is mod S square plus mod B square, which is 1 I have taken for determinant 1, and it is unitary. That you can check. You check, just you check this. This is unitary if this condition has to be satisfied. U dagger should be 1001. That 1 will come because of this relation. And you can check that all this for parameterization or this parameterization in independent parameterization satisfy this property. So this is a general way of writing, another way of writing, not a parameterization, but a small, compact way of writing this unitary matrix with the extra condition. In that sense, it is not a parameterization. A and B are not independent here. A and B are dependent by this. But you write it for your calculation to bring, to put you in some calculations. Often we do this because that later we will put you A equal to something, B equal to something. Okay. So do this thing. So, okay, so do this thing means, so this thing, see, this object is what? This object is xi into u sigma I u dagger. Clear? Because xi is a number, it comes out. So three things we have to calculate. One is x u sigma 1 u dagger, x2 into u sigma 2 u dagger, plus x3 into u sigma 3 u dagger. ঠিক আছে? Expanding it. Okay. So let's calculate one thing. I will calculate one object, and so that the things you can follow later and write down the other expressions directly. We will not calculate, you can calculate it. So
X are you commute করে, right?
huh?
X আর U?
কোন X?
XI, this one.
XI তো একটা রিয়েল নাম্বার।
Oh, okay. Sorry.
Sorry. So calculate U sigma U dagger 1 for first Pauli matrices. For every Pauli matrix I have to calculate this. For U I will write A B minus B star A star, where mod A square plus mod B square equal to 1, that is implied. Clear? Because this is one form of U. Sigma 1 is this, and U dagger is dagger of this matrix or inverse, whatever you call. So dagger is dagger is what? A star minus B transpose and conjugate. B star. Clear? ठीक है?
Yes, sir.
So now you multiply it and then multiply it. I am writing the result. This product of 3 multiplication I have in the back of this envelope calculation. You can do it. So there's 3 A B star plus A star B A square minus B square, A square minus B square star minus A B star plus A star B. ठीक है? So if you multiply this, you will get this. This is trivial. Now see, suppose there are any matrix P Q R S, any 4x4 matrix, any 2x2 matrix which is traceless. Traceless means P should be equal to minus S. P and S should be opposite here. So it is a traceless matrix because this is obviously a traceless Hermitian matrix. Sigma itself is a traceless. U sigma U dagger should also be traceless. You can see this directly from here. This is a traceless matrix and a Hermitian matrix, obviously, of the order 2x2. Then this matrix can also be written in terms of sigma 1, sigma 2, sigma 3 only, because it is a traceless Hermitian matrix and sigma 1, sigma 2, sigma 3 matrices are the basis of this. And you can write this, any general matrix, you can write it which way? What should I write? Can anyone? So if I write it as a linear combination of this, what should be the coefficients of this? Anyone? Can you remember this? These things you have to remember every time, because now you are doing such kind of mathematics. Every time you have to check, it is difficult. Okay, so let me do this. So PQRS, I also don't remember actually. C1 is, so it is C1 into 0 1 1 0 plus C2 into 0 minus I 0 plus C3 into 1 0 0 minus 1, which is equal to C1 plus C3 C1 minus IC2, C1 plus IC2.
স্যার ফার্স্টের টার্মটা C3 হবে না শুধু?
Oops, sorry. C3, last term to have minus C3. Okay. So you know C3 would be P. Okay. C3 would be P. If you C3 is P. C3 is P or minus S. C1 plus IC2 is Q. C1 minus IC2 is Q. C1 plus IC2 is R. Then what? Then what is C1? Can anyone tell me just what is C1 and C2? Can anyone just tell me in terms of PQRS? C1 plus IC2 is Q. So twice of this 2C1 adding this 2 will be Q plus R. So it is C1 is Q plus R by 2. And if you subtract this 2, you will have minus 2 IC2, which is Q minus R by 2I. So by minus 2I. So I Q minus R. Is this okay?
Yes, sir.
Now this matrix, so if you want to write it in terms of something plus sigma 3, you have to write these coefficients. These coefficients will be C1. C1 is Q plus R by 2. So this, they are plus by 2. Okay. So it should be real part of A square minus B square. Is it clear? This to sum by 2. Sigma 2's coefficient will be Q minus R by 2 into I. So Q minus R is this. So this is Q minus this minus this star is what? Imaginary part of A square B square by 2I multiplied by this I here. So it will be minus imaginary part of A square minus B square. And sigma 3's coefficient C3 is just this P. So just this number. And this is A star B. A star B means this is, you can write twice of real A star, AB star or A star B, whatever we. Is this clear? Sorry. Clear means a straightforward calculation, but you know how to do it. Just understand how to do it. Then you can check later. বোঝা গেল?
Yes, sir.
Yes.
So in this way, I can do it again for sigma 2 and write it in terms of AB and then write the whole matrix in terms of sigma 1, sigma 2, sigma 3 linear superposition and get the coefficients. Okay. So let me directly write down the coefficients. It is up to you to check it. Don't believe me. Please check later. But for I have to do things. So these things is a real A square minus B square sigma 1 plus minus imaginary A square minus B square. Actually, once you have to do this calculation because you don't know when and where this calculation tricks will be available. A, B star or A star, B, whichever way you think, sigma 3. Similarly, U sigma 2U dagger is, you can check this. I have not done this. I just have the result. Sigma 3. Clear? Clear means to check this, but this is the result you will get. Now, what is x prime is x u, sorry, u x u dagger, which means x I prime sigma I is equal to, as I said, this xi u sigma I u dagger. This relation we got earlier. This is this relation. Now, in place of these three objects, for 1, 2, 3, you put these three. So everything will be in terms of, for first one there are 3 terms, for second one there are 3 terms. So collect all the sigma 1, all the sigma 2, all the sigma 3 1 together, and this thing you can write as some number into sigma I. Clear? This star I will contain all these terms. So this star 1 is how much? x1 into this plus x2 into this plus x3 into this. Okay, so you can see this also directly. So we can write now we can write this matrix x1 x2 x3 prime 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 is equal to real part of a square minus b square. This is imaginary part of a square plus b square 2ab, this thing ab star. This is a very important relation to understand the entire business. সব ল্যাটেকে লিখতে গেলে আমার জান কয়লা হয়ে যেত। Is this steps clear? Calculations I leave it, but you can directly see that x1 here from this relation x1 prime will be this x1 into, because the coefficient of sigma 1, so x1 into coefficient of sigma 1 is this here in this expression, plus x2 into coefficient of another sigma 1 comes from second relation, so x2 into that, so this, sorry, this clear? Is this okay? Or you can look at it and see what I have done. So A, B are parameterizing this matrix U. Now, using this relation, I have written x prime, y prime, z x prime, this vector in terms of the untransformed original vector after transformation by this matrix. This matrix obviously should be an SO3 matrix, rotation matrix, 3x3 rotation matrix, but written in terms of elements of SU2. A, B are elements of SU2 matrix, a particular SU2 matrix elements of a particular SU2 matrix. Is this clear? If you use this relation and use this, you will get this. Hello.
Yes, sir. Okay. Well, I think there are some problem of minus sign.
Huh?
So minus sign are.
Oh, okay. Check it later, because
Yes, sir.
it may be my problem, maybe your problem, maybe not. Now come to this. Okay, where is this? Look at this transformation. So instead of choosing these three, only choose this U matrix. If you choose this particular submatrix as U2, parameterized by one parameter here. So it is not all SU2, only one class of SU2. So multiplied by 3 will give you all the SU2 matrices. So take this matrix. So if you take this matrix, what is map with A? What is A for this matrix? A is e to the power minus I alpha. And B is 0. Okay. Correspondingly, established will be accordingly that. So A is e to the power minus I alpha, B is 0. So what you do here, you in this equation, put A equal to e to the power minus I alpha, B equal to 0. Is it clear what I am doing? Take one particular matrix. Sure. So take U belongs to SU2 as e to the power minus I alpha 0, 0. A particular choice with one parameter, which corresponds to A equal to e to the power minus I alpha, B equal to 0, because any general U we have parameterized as this. Okay, now so what I am doing here is that I am taking a particular subclass of SU2 matrices, a particular type of SU2 matrices, not all, doesn't represent all SU2 matrices. Only product of these three will represent all SU2 matrices. So the first one, so not alpha, say gamma I have taken. So let's take gamma. It is equivalent, same. Let's take gamma. So it is gamma. Now what I am taking a particular SU2 matrix and trying to find out what will be the corresponding SO3 matrix, which is homomorphism. So here I have to put A and B. So if you put A and B, put B equal to 0. So A square, real part of A square. So what is that matrix? So I am taking this R for, say, I am writing this as R for this matrix. Clear? This is the argument of this matrix. So it is saying that if I choose this particular U, what will be the corresponding R? That is the notation. Now A is e to the power minus I gamma. That means A square will be e to the power minus 2I gamma. Who's the real part? B is 0. Whose the real part is what? First term will be cos 2 gamma. Is it clear? I am writing this matrix. So first term will be cos 2 gamma. Can anyone tell me what will be the second term? For A equal to e to the power minus 2I, sorry, A হচ্ছে e to the power minus I gamma. B হচ্ছে 0. What is the second? What is this term? Just do and see.
cos 2 gamma.
No, cos. It's very many.
Sin 2 gamma.
Oh, minus sin 2 gamma.
Minus sin 2 gamma.
Then what is this? What is this?
0.
1.
0, because B is 0.
Oh,
So real part of 0 is 0. This is 0. This is 0. This both are 0. This 3 cross 1, 3 cross 2 are also 0 because it involves B. So in place of here I write 0, 0. What is this? Because B is 0, it is mod S square. Mod S square is 1 because e to the power I.
yes.
What is this too? Imaginary S square.
So the 1, 2 element will be negative, I think.
Yeah, sure. So something will be negative for this choice. It should so either here or here.
The 1 to 1.
Say 2-1. I think 2-1.
Yeah, it should come like this. Because this we say from our intuition. Clear? So if you choose this matrix, this particular type of matrix, which is not all SU2 matrix, only one particular class of SU2 matrices parameterized by this kind of transformation, this kind of matrices, then the corresponding matrix R, SO3 matrix, is basically this matrix, which is a rotation about what axis? Z axis. Clear? So this is, so I get this thing. E to the power minus I delta 0, 0 e to the power I delta. This is cos delta, sin delta 0, sorry, sin gamma, 2 gamma, sorry. So that is, this 2 is very, very important. So this 2 will make it, I mean, this because of this 2, this homomorphism will not be isomorphic. It will remain as a homomorphism. I will come to that. Okay. Now consider this and consider this. Take this matrix where A is equal to cos beta, B is equal to sin beta. then can you tell me if A equal to cos, both are real? So which terms of this will be 0? The terms which contain Im, these terms will be 0 in this matrix. Clear? Because A, B are real numbers.
And
So,
B will be minus sin beta, I think. In that case, you have written A equal to cos beta, and B it will be minus sin beta or sin beta.
Okay, right, minus sign. Okay, minus sign. Okay, that is immaterial. You could have written minus sin beta here also. Okay, minus sin beta. Then this matrix cos beta minus sin beta cos beta. Corresponding matrix will have a structure 0, 0, 0, 0 here. Okay, because imaginary parts are sitting there. Now at the center, a square plus b square. Okay, so a square b, so a, b are sine and cos. So sine square plus cos square is 1. In this part, it is cos square beta minus sine square beta. Clear? Here it is 2 into real part of AB. AB are both real, so minus 2AB. Minus 2 sine beta cos beta. And you can check this. Clear? ঠিক আছে? All that is remaining is this matrix. Okay? Alpha. So here A is cos alpha, B is I sin alpha. This is involved. So because or A is real, B is purely imaginary. Okay. Now you can check that for this here first term is what? Cos square theta plus cos square alpha. Because of this minus will become plus, I square will become plus. This is 1. Okay, so for this cos alpha I sin alpha cos alpha, first term is 1. This term is what? This term is what?
Zero.
Yeah. Cos square alpha minus I square, yeah, because it is pure real, a square b square is real, then it is 0. Next term is also 0. Because a b is purely imaginary, so a into b is purely imaginary, its real part is 0. So also this is 0, because this is real part of a b star, it is purely imaginary. A square plus b square, you can check, this is real number, so it is 0. And this term will be one term, if I calculate is enough. A square plus b square is cos square minus sin square, so it is cos 2 alpha, and this part, imaginary part of AB is 2 means plus sine 2 alpha cos 2 alpha. This minus sign will come because this B star is there. Now is this so? This calculation is cumbersome, but do you get this point at the end of the day? You choose 3 specific SU2 matrices, all are linearly independent parameterizations. Corresponding to these 3 parameterizations, we have found out what will be the corresponding SO3 matrix, which is related to this SU2 matrix by the way we described, by vector space and TH2 space. Is it clear?
Yes, sir.
Now you can take the product of these 3. This product of these 3 is a general U3 SU2 matrix. Correspondingly, you can take this product of these 3. So that is a general SO3 matrix. Keep the order same. So product this into this into this, then you take this into this into this. Then you can find out, given alpha, beta, gamma, you can write down a SU2 matrix as well as SU3 matrix. Clear? So let's have this equation in at our front. So okay, just I'm changing a pen. Just tell me whether these write-ups are clear. This is another pen is e to the power minus I del 0 0 e to the power. For this product of these 3 corresponding, this is not equal to, so this is the mapped into this homomorphism. So this is U written in terms of gamma, beta, alpha, and this matrix R written in terms of same parameters. So given 3 numbers, you can write down a SU this belongs to, and SU2 this belongs to, and SO3. And this shows you these 3 parameters. You can either look them as a unitary matrix parameterizing, or SU2 matrix, or parameterizing another SO3 matrix. So there is the connection. Here is the connection. Clear? Now, so can anyone, what information I can extract more about this? If you write it gamma by 2, beta by 2, alpha by 2, here it will be gamma, beta, alpha. Okay, say you can also write that. Now, suppose you have a vector in R3, any vector. Now, any vector by this rotation matrix will be rotated by 3 angles in 3 planes, alpha, beta, gamma in 1, 2 plane, 2, 3 plane and 3, 1 plane. After that, it will come to a new position. Now, if you want to encompass all possible rotations, how much will be the variations of these angles? Alpha equal to 0. Here, alpha equal to 0, beta equal to 0, gamma equal to 0 means identity. Then you see everything becomes identity. This matrix becomes identity matrix. There is no rotation. Now you are changing alpha, beta, gamma independently and simultaneously by your will. You do not bother whether how much you are changing alpha, how much you are changing beta, but you are slowly changing from identity. And you are moving from this, rotating this vector from 2 different planes in 3 dimension. Now, if you want to encompass the entire 3-dimensional space just by rotation, your alpha, beta, gamma are continuous parameters. When for one complete encompassing the entire space, over how much range you have to vary alpha, beta, gamma? Can you tell me?
SO2 তে 02 পাই যাওয়া মানে SO3 তে পুরোটা কমপ্লিট করে নেব।
Yes, right.
না SU2 তে পাই যাওয়া
মানে পুরোটা কমপ্লিট করতে 2 পাই ঘুরবে অ্যাঙ্গেল গুলো। This whole angles, this 2 alpha will range from 0 to 2 pi. Okay, that means here it is alpha. So what should I say is that if alpha, beta, gamma, all these varies from 0 to pi, see clearly, if these 3 parameters, this picture I draw, if these parameters vary from 0 to pi, okay, then because it is the argument cos of 2 gamma 2 beta is there, so you will get at pi, alpha, beta, pi, you will get again identity. You see, because you are getting cos 2 pi sin 2 pi. That means from identity you are varying and the entire space is being accommodated and you are coming back to again identity. So all that means by varying these parameters from alpha this way, alpha, beta, gamma 0 to pi, you are generating all the parameters of all the elements of this group SO3. No element is left. If you vary the continuous variation from 0 to pi, 0 to pi, 0 to pi, these 3 parameters, for each value of the parameters within your range, there must correspond to one element of this, and all this 3-dimensional space will be traveled by your rotating vector. No space is left. That means all possible rotations in 3 dimension are captured by this range of variation, because 2 it is sitting, 2 gamma 2 alpha is sitting there. Is it clear? Now, hello?
Yes, sir. Clear.
Now, if alpha, beta, gamma varies from 0 to 2 pi, the question is whether all elements of this SU2 group are generated. Parameters are useful for generating different elements of the group. Now I am varying this over this range. Now if so what is the element corresponding to what is the SU2 element corresponding to alpha, beta, gamma equal to 0? Can you tell me? What is the SU2 element, this matrix, SU2 matrix corresponding to this 0? Tell me.
Identity.
Identity. Yeah. Now, what is the element corresponding to pi? The question is, it is identity or not? For pi, for alpha equal to pi, this is cos pi, this is 0. So minus 1, 0, 0, minus 1. So you bring minus 1 here, leave it identity. So drop this matrix and carry 1 minus sign. Now for beta equal to pi, again there is an extra minus. There is 1 minus sign, this is minus 1, 0, 0. So this 2 minus 1 will make it positive. So this product is identity. So you are left it only this. This is for gamma equal to 0. Is it identity? Yes. Am I saying correct?
So, sir, as a whole,
Yes,
we
sir.
will get minus identity.
Hmm?
Combining the three, we will get minus identity.
That's why I'm checking. Please check.
Yes, it's
I'm getting something different.
No, sir, it's plus identity.
There is some problem. Just a minute. Uh, for oh, just a minute. Just let me think. There is some problem. We expect a minus identity here. Oh, maybe we should not write it this way. If alpha, beta, gamma were pi, all is equal to pi, then what is this matrix individually? What is this matrix? Okay. Just a minute, 1 second. So e to the power minus I gamma 0, 0 e to the power I gamma. Suppose gamma is 0 here, gamma is pi here. So it is, this matrix is, for gamma 0 it is 1 0 0 1. For gamma equal to pi, this matrix is e to the power I minus I pi. What is e to the power minus I pi?
minus
Minus
1.
1.
Minus 1.
Minus 1. This is also e to the power I pi is also minus 1, right? Okay, let's see this way. Matrix of the So for beta equal to 0, this is identity. For beta equal to pi, this is how much? For
Minus
beta equal
identity.
minus identity. For cos alpha, I sin alpha, I sin alpha, cos alpha. So this is strange. Oh, that's why it's coming. No, what is this? Is it clear? Is this coming?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Oh, then what was the problem? Oh, sorry. Oh, someone misguided me. So their product should be minus 1, because this 3 at pi, at alpha beta pi, even if you individually check, when both are equal to pi, this is minus identity, this is minus identity, this is minus identity. So their product is minus, this is minus identity, this is not identity. Clear? So this thing becomes minus I. Is it clear? We did some silly mistakes here earlier. Clear? When alpha beta gamma is equal to pi, then SU2 matrix becomes minus identity. This is clear. Not only that, just we have checked each of these SU2, each of the separate independent parameterizations of SU2, subclass of SU2, they are becoming minus identity when all these are pi. Okay, but they are corresponding matrices. This one at pi becomes identity. Okay, now see this. I will end with this. Look at this. That means when as alpha varies from 0 to pi, you move from identity matrix in SU2 plane to minus identity matrix. Okay, now obviously this does not encompass the entire SU2 space. All the matrices of SU2 are not generated by this variation. How many matrices will be generated by this? Whatever is there, it is not how many, because this group is infinite. So half of the group, you can say, you can cover by this movement, identity to minus identity, by moving this. So this structure is like this. Basically, you have this, say, SU2 group. Okay. Now having 3 parameters, gamma. Now you varying, this is, so these are, suppose these different elements of the group are like this. So this is identity. And this is suppose minus identity of this element. Now if you vary alpha, beta, gamma continually from their 0, 0, 0 values, you move from here to here, only half of this group is generated. Is it clear? Rest half remains. When you move from pi to 2 pi, then minus, it will come back from minus infinity to plus infinity, generating rest elements. Is it clear? You vary from alpha 0 to pi, half of the SU2 group elements will be generated, because this is because these periodicity of these functions here are 2 pi. So you move from 0 to pi, so only half period you have covered. Rest, to come back to it in the same position, it has to move from pi to 2 pi. So if there is, or say, let's write this. So this is SU2. If you move, this is SU2. If you move from 0 to pi, all these parameters you vary, then you covered half of the elements of this group. But so there is a SO3 group. If you move from 0 to pi, because there are 2 sittings here, all the elements of SO2 groups will be generated. Come back to this. Okay. Now you move from this to this. So that pi to 2 pi. So that rest of the elements of SU2 are generated. And what will happen? SO3 group will again be generated. Clear? Is this idea clear? If you move alpha, beta, gamma from 0 to pi, all these parameters, half of the elements of SO2 group will be generated, and it will move from identity to minus identity. Then you again, then SO3 group will be fully generated, because it is 2 alpha, 2 beta, 2 gamma sitting in the parameterization. Therefore, those parameters have completed their full period. 2 alpha moved from 0 to 2 pi, 2 beta from 0 to 2 pi. Now again you move from alpha, beta, gamma from pi to 2 pi, so that periodicity in SU2 is completed. Then SO3 will be again generated once more. So this is the that means, what does that mean? Does that mean corresponding to every element of SU2, there are how many elements of SO3? Other way. Corresponding to every element of SO3, there are 2 elements of SU2. 2 elements of SU2 are mapped into 1 element of SO3. Is this clear from here? Why I am saying is because if you change gamma, alpha, beta, gamma by pi minus alpha, beta, change alpha by pi minus alpha, gamma by pi minus gamma, beta by pi minus beta, then this matrix will not change, because cos of 2 pi minus 2 alpha is same as cos 2 alpha every time. Here it will change because you are changing. Is it clear? No. Or should I stop again? And okay, let me stop here today. You think this out, and next day we can catch it from here. This is a very involved and crucial idea. For every element of SU2, for every element of SO3, there are 2 elements of SU2. Can anyone see this? Because, hello? Am I audible?
Yes, sir.
Okay, so we'll come to this, but just for before next class, just try to find out that what I have done up to this point. Its interpretation I will tell, because today is ending, and you can just change alpha to pi minus alpha, and can check that both for alpha and pi minus alpha, this matrix remains unchanged, same. But this matrix will not be same. That means there are 2 different matrices which are mapped into one matrix. There is a 2-to-1 mapping. Okay, I will continue in next class. I am sorry for today's clumsy calculations, because without this I could not have done this. So SU2 to SO3 is a homomorphism, not an isomorphism. Okay. Okay, let me stop here. Any questions you can ask, or up to, I mean, what is this calculations clear? What I have, how I have reached here, from here to here?
Yes.
Okay, so okay, let's stop here. You can ask if you have anything to ask. Are you having headache?
No, sir. No, sir.
No, it is okay if you have a headache. Actually, I am having headache. But please try to do these work out these steps, whatever I have done, to reach here very thoroughly. Otherwise, you will miss the beauty of this thing. You will miss many things. Just try step by step what I am doing. SO2 to SU2 to SO3 for this, establish this mapping, whatever I am doing, and at the end of the day, how I mapped it here. Okay. Okay, so next day we will see this. Because of these 2 factors, and there are periodic functions involved here. So corresponding to, there will be 2 different values of these matrices, for which there will be one matrix here. Okay. Okay, let me stop here. That's enough for today. Thank you.